Okay, so recall. So if I have what this is, generally speaking, A and B are all models in our model. And a typical element looks like this. Where AI is in model A and BI is in model. So it's just a sum of the symbols and the R action. For R and sum, right? And first one is sum. You can bananas, right? The tensors are subject to the relation. And so first of all, we built this crazy quotient group, right? Here's what I forced on it. Those relations hold. And 3, so we have this from the relations, and we can define, as I pointed out last time, this. Define DR action. Okay. So let me point out some of the kind of weirdo things here. Now remember, a tensor product is first and foremost, I mean, a free ability group, it's quotient. So technically, each one of these separate tensors is the coset AI comma BI plus K, where K was that crazy figure I modded out by. This is a shorthand notation for this. Let me point out that because if you look, this is right, by rule number, I guess, 1 up there, right? Because we've got the same X, we can combine here. This is A plus 0 tensor X. This is an abelian group because it's a quotient of the abelian group. So that means that this is a 0 element, right? Well, there's nothing special about this. That's the 0 element as well. So let me give you an example. So let me actually write down the tensor. And this shows some of the, maybe it will point out some of the difficulties of working cosets. Well, that's easy enough, right? Because I've only got finitely many tensors, right? Tensor number Z. The tensors are That's it, right? And guess what? 3 out of 4 of them are zero, right? By this observation here. These are all the same thing. They're the zero element. So first and foremost, a tensor product is an abelian group. So I know what this is. I've got it down to 2 things. This is either the zero group, right? If that last tensor is also zero, or a Z2. That's it, right? This is actually isomorphic to Z2. Which may seem kind of weird, because why would I write this fancier thing, Z2? I haven't proved that that's not zero, but we'll see that in a moment. What about this one? I'll write Z2 this way. I'll write Z3 this way. Separate. There's only 6 tensors here, right? So I've got 0 bar, tensor 0 star, 0 bar, tensor 1 star, 0 bar, tensor 2 star, and then the ones. 2, whoops, 1 tensor 1 star, and 1 tensor. Now, I've got several that are 0. In fact, I've got a lot of them. So what do you think for this one? This one's 0. These last 2 tensors are 0. Not obvious, right? Somebody know why? Let me point this out. Well, actually, let's start with this one. This is 1 tensor 2 and 1 star, where 2 is an integer, right? So this is an integer, so I can pull it across the tensor. Right? And this 0 bar tensor 1 star. Right? I mean, I put a little slime in trap, but I mean, like 1 bar. This is 1 bar tensor 2 times 2 star, isn't it? And you can do the same thing. So with all my fancy writing, this is just 0. Let me point out something else. This is why weird things can happen. I know what I mean by origin.
Everything's finite order.
Right, the T may be an infinite group actually, but every single element in there has finite order, right? So for example, T might be an infinite direct sum of Z2. It's like this. When you potentially Q it goes origin. Now let me give you a quick proof. The way this is zero is, of course, everything in this tensor product is a sum of tensors, right? Single tensors. So if every single tensor is zero, I think we would have to agree that this has to be zero, right? So, consider Q tensor to be a single tensor. By hypothesis, there exists n in the natural numbers such that NP is zero because the group is torsion.
Just divide Q by N.
That is correct. So if you look, Q tensor T is N times Q of N tensor T. See how sneaky I am? Now slip this N across the tensor. So every single tensor is zero. So what's generated by a bunch of zeros is zero. So there's perhaps more than meets the eye. Now, so what's the big thing about tensor products is this.
Could I ask first, so does it have to be Q, or does it have to be division ring, or could it also be a divisible?
That's a good observation. Yeah, if you tensor, yeah, all you need really to make this work is for you to be able to divide that first coordinate by any n natural number. So in particular, if you tensor with a divisible group, divide that work. So uh, remember, it's math. It's easy. What's the easiest way to get an element of the Cartesian product? Easiest way to associate tensor with that?
Assuming the state's on A.
I claim that this is about linear. I'll at least give you a taste of this. If you look at this is A1, it's A2, tensor B, A1 tensor B, that's A2 tensor B, which is our A1 B, and same in the second coordinate. Group is the same. Also, if you have which is so this map is bilinear. This is going to play a role in our next theorem. The tensor product comes sort of naturally as a solution to a mapping problem. But this time, instead of talking about homomorphisms, we're talking about bilinear maps. So let me give you the statement of this theorem. If A, B, and C are R models, and let's have a function, G from A cross B to C. Be bilinear. Then there exists a unique R-module homomorphism. There exists a unique R-module homomorphism. Let's call it G bar from A tensor B and C, such that G bar iota as equal. So in other words, you can this the homomorphism, you can actually sort of turn this bilinear map into a homomorphism in a certain sense. Where iotas we have 4. One we talked about earlier. The tensor product is uniquely determined at the isomorphism. Let me draw you a obligatory picture here. If you have iota, then this list of an R-module homomorphism makes the diagram. Okay. This is a great theorem. And I'm here to tell you that whenever I want to build a homomorphism, if I want an R-module homomorphism from the tensor product somewhere else, then I almost exclusively use this theorem. Can somebody tell me why this is powerful? Suppose I wanted to build a homomorphism from A tensor B into some C. Why does this theorem make our lives easier?
You only need to have a bilinear map from the product.
That's exactly right. Determining a map from just a Cartesian product is bilinear. That's not too bad. From scratch, saying that you have a homomorphism from A tensor B and C, that could be quite difficult, right? Because what's the first thing you've got to do? You got to show the thing's well defined, because what it is it's a quotient group, right? So when I talk about even a single tensor, I'm talking about a coset. Is that even well defined? And hopefully my examples earlier showed you that sometimes it's even difficult to tell if a tensor is 0 or not, right? So you're going to have a heck of a time doing that. Whereas if you could just lift it from a bilinear map, that's a lot easier. So it seems like it would be worthwhile to have this theorem, and so we better prove it. And then I'll implement this with a few examples. You can see how this works. So proof. But yeah, be pretty good on A cross B and A, the subgroup defined earlier. So it's just that subgroup that's designed to make those relations hold. in the quotient. So the map, P, A, B, and C is bilinear. By assumption. We're assuming that, of course, and it induces a homomorphism. G star, say, from F into C. Right? Because remember, this is a free abelian group, right? So it's a free Z module. So all you gotta do is find its basis, which in this case is A cross B. And the bilinear map is basically what's telling you where to send every basis element. And so, as we've seen before, this is the set map that we need to induce a homomorphism. So given G tells every basis element where to go over here in C, because it's just my bilinear map. And that induces a homomorphism because this is free. So once I know where the basis goes, I understand the entirety of the homomorphism. So, since G is bilinear, and this takes every element of, well, G star takes every element of K in zero. Remember what K was. K was generated by things that look like A1 plus A2 comma B minus A1B minus A2B. So the fact that G is bilinear means that this induced homomorphism has to take every one of those things to zero. So in other words, the subgroup is contained in the kernel of G star. And so this means, since K is contained in the kernel of G star, we use our isomorphism theorem. So this induces G bar from F on K into C, since G bar was contained in that, or since K was contained in that kernel G bar. And so in particular, and if you look at G bar iota of A comma B, which is G bar of A tensor B, right? Which is G of AB. So in particular, G bar iota. Now, how about uniqueness? Well, uniqueness is actually not too bad because if there is another such homomorphism, H, goes from A to big C. Let's say this is a homomorphism such that, H on the A tensor B is G of AB. Then what can we say? Then H and G agree on tensors. H and G bar, that is, agree on every single tensor. And of course, everything in the tensor product is the sum of these, and so if these homomorphisms both agree on every single tensor, then they have to be the same. And I will leave it to you to see why this must be unique up to isomorphism. Okay, any questions? Let me give you an example here. Um, let's see if we can prove that. If you look back at our examples, we proved that Z2 tensor Z3 was zero. And that was easy enough because we showed that every tensor was zero, even though it might have been a little surprising. It's probably less surprising than Z2 because what we had is when we computed all the single tensors, we got three of them that turned out to be zero. And then we had a one bar tensor, one bar, didn't look like zero, but then neither did some of those others, right? Here, iota, where it takes the order pair just to the tensor. I need a bilinear map here. G. I think, I guess that will, have
Just
to be,
choose the first one.
say that?
You just choose the first one.
Well, yeah, all of those I think will be bilinear maps, but I want something that, how about this one? Right, I think that sort of more mimics what we were going on perhaps. In fact, let me just call this A, and that'll be, so I don't confuse myself later. Does everybody believe this is bilinear? Right, because when you replace A with A1 plus A2, You distribute it out and what you want, right? Everybody okay? Right. So this is a bilinear map. So there exists P bar such that, when you do iota and G bar, it's the same thing as doing G. Right. Bar going from G to tensor. Now, what happens to G bar of AB? I mean, I can tell you exactly how this map works, right? A tensor. So if you look at a single tensor, tensor B, this comes from AB. Everybody agree? And that goes to AB. So here's the way the map works. It's very much like a product. Is it clear to you all that this map is onto? Right? So that now I see that my one tensor one that I wasn't so sure about before actually goes to one. Right? And here's the bonus. If I did this homomorphism from scratch, I would have to go through and check that that is a well-defined homomorphism, which is obnoxious because that brings us back to the problem we had in the first place: is one tensor one zero, or is it not zero? Right? So here, there's my homomorphism. Are you okay with that? Here's another one. Here's another example.
Oh, could you just say the conclusion now? So that homomorphism tells us the.
So G bar is onto and 1 to 1, right? Because G bar actually had 3 zero tensors, and it only had one potential non-zero. So the order of this was less than or equal to 2. So it's got to be one. It's got to be 1 to 1 as well. Okay, so C2 tensor C2. Here's another one. Okay. Let A be non-natural. Then and in fact, there's a more general thing. Turns out the tensor product is very much the direct sum. So in general, if you tensor A with a free module of some rank, say n, then this is n copies to A. Okay? Well, let's just do this. All right. Again, it's difficult to set up a homomorphism from here to here, or I mean, you can set up one from here to here, but then how do you know you've covered everything, et cetera, et cetera. So let me go back to my trusty diagram here. Now,
We're just going to make it our action.
here we go. So I just take the order pair AR to RA, right? Is it clear this is bilinear map? place R with all of R2, place A with A1 plus A2, and so forth, right? This is so what do we have? My theorem 683, we have R module homomorphism. Say G bar from A R into A, and it's given by G bar. Well, let's just follow our nose here. A tensor R that comes from AR, which goes to RA, so this has to go to RA. Multiplication. Anybody else use it? Now, let me go through a little bit more detail here. Okay, good for us. You've got the homomorphism here, and that's how it works. You draw the diagram again. Oops. A tensor R goes to R. So, okay, okay, well, A being A, how about this? G bar of A tensor 1. There you go, it's on today. How about 1 to 1? Well, let's suppose G bar, well, actually, yeah. Yeah, I'll do this. Let's suppose that you have a single tensor in the kernel, right? And this is RA. This means that R kills A, right? So now somebody explain to me why my proof is incomplete.
General elements, tensor, product homomorphism.
Problem. So I have totally vanquished this if it were true that every element in this particular tensor product is a single tensor. However, how do you know you don't have something more complicated? But in this case, you don't. Now observe. What does a typical element look like? A1 tensor R1 plus A2 tensor R2. AK tensor RK is in. I claim it's a single tensor. Because there's something special going on here that allows me to do this. Check this out. This is equal to R1, A1, tensor 1, plus R2, A2, tensor 1, plus RK, AK, tensor 1. Right, and just like we're on Lawrence Welk, we break out the accordion, and R1, A1, R2, A2, RK, AK, tensor 1, which is, let's say, R tensor 1. So every element of A tensor R is a single tensor. And in fact, not just that, it's a single tensor where you can choose one to be say coordinate. You like. And that shows that this proof is complete because proving it for a single tensor is good enough. Okay, any questions? Yes,
Is that almost enough to prove the isomorphism you were looking for?
what's in that?
Yeah, that last observation, is that almost enough to prove the isomorphism between?
Almost, as
Yeah.
long as you know that these are non-zero, as long as this is zero, right? Or as long as this is not zero, and that tensor is not zero, if you know that. Okay. Questions? So. Are you guys okay?
No. No, I was wondering why in the last line is RA and not A only.
Oh, just, for dramatic. It could be yeah, that's fine. Okay. So let A prime, B prime. B prime. These are all R modules. And F from A, G, B prime, the R module homomorphism. Then there exists a unique homomorphism. Homomorphism. And this is, so I'll give you a notation for this. This is often called sometimes this is just called the tensoring of the two. It's a handy notation, such that, F tensor G notice all I have to do is tell you how this behaves on tensors, and then you know how it behaves everywhere. This is equal to F of A tensor G of B. So you do F to the first coordinate, G to the second coordinate, and this is called tensor product, and you expand this by linearity. And then you let me prove this nifty corollary. Briefly. We're trying to go from here to here. Okay, so to do this, I need to build myself a bilinear map from here to here. What do you think? What's it?
We are already using G.
Verify that this is bilinear. Oh, I see what you're saying. Hello, how about calling this Captain G? So this is a bilinear map, right? So if you, look at, I'll just do one demonstration of this. If you look at G of A1 plus A2, B, this is equal to F of A1 plus A2, G of B. But of course, these are assumed to be, R module homomorphisms. So this is F of A1 plus F of A2, GB, which is F A1 GB plus F of A2 GB, which is big G of A1 B plus big G of A2. Et cetera. The others are very similar to this. So G is bilinear, and so it induces where, and of course, this is what we define to be, at tensor G.
So we're using a different notation there. Because this should be tensor rather than addition.
Right. Is that what you meant?
In the last two lines of this,
Last two lines here, what did I do?
the addition sign must be O plus.
What are all here? So this is,
The image of G should be a tensor rather than an ordered pair.
oh. Thank you. So this should be, oh. Yeah. So this should be. Yeah, right. So this is, yeah, thank you. So this should be, F available, say, two tensor. Right, which is F A1 plus F of A2 tensor GP, which is F of A1 tensor GP plus F of A2 tensor GP, which is G of A1 B, right, plus G of A2. That is correct. Okay. Now let me, I'm going to give you a preview for the next time. And this might be kind of surprising as well. The tensor product is sort of dually related to hom. this probably looks similar to a hom, as you're saying, right? It turns out that this is exact if and only if, you get exactness here, right? This is called right exact, because here we preserve the onto, but not necessarily one-to-one. Okay, we'll talk in depth about that next time. Any questions?
A question?
Yeah.
How can you use abstract algebra to solve the Rubik's Cube?
Oh, you'll have to see on Friday.
Glad you asked.
Yeah, so yeah, what I'm gonna do in Friday should be kind of fun, because we're gonna do symmetric groups, just baby stuff. It'll be pretty computationally, that'll be it. I mean, this is a talk that I wouldn't flinch at giving to, somebody in high school that was eager about it. So it shouldn't be too hard. There'll be a little bit of group there, but you'll see how to solve the Rubik's Cube, in fact, make shortcuts. Oh, and also I've talked to the Zoom people, and they're still, apparently they think that our Zoom recording from last Friday is in Amelia Earhart's airplane, and they're working on getting it back. Hopefully that will come soon, so.